EDX Decision 1 Linear Programming, Formulation and Graphical Solutions. Graphical solution using the vertex method. For linear programming problems with two variables, we can plot a graph to solve the optimization problem. Each constraint is a linear inequality. We draw a straight line for each one and then shade out the unwanted region. This leaves us with an unshaded region of possible solutions, which is called the feasible region. Okay, so I'm going to work through a few slides. I'm going to do one constraint on each slide so we can see what's going on. I wouldn't normally recommend drawing all the lines on together, as you can see here. Normally I would recommend just putting on one line at a time and dealing with it, but this is just a restriction of the recording. So the first one I'm going to do is this one here. So we draw the line y equals 3, which is this horizontal line, and we need y to be less than or equal to 3. So y can be smaller than 3 or it can equal 3. So in other words, y can be anywhere on the line or underneath it. So I would lightly shade out everything above the line y equals 3. You don't need to do the shading too heavily, just nice and clearly. If we look at the next constraint, x is less than or equal to 3. So you draw the straight line x equals 3, which we have here, x equals 3. X can be less than or equal to 3. So x can be 0, 1 or 2. It can be any value smaller than 3. So we shade out the region we do not want, which is bigger than 3. Okay, and then I'll move on to the next constraint. So now we're looking at this constraint. Y is less than or equal to 4x. So we draw the line y equals 4x, which is this line here. Now sometimes students struggle with straight lines that go through the origin. They're not sure which side to shade. One method is to just pick a point on your diagram. For example, let's pick the point 2, 2. So I'm going to pick that point 2, 2. Is it true that 2 is smaller than 4 times 2? And the answer is yes, it is. So that point there is on the correct side of the straight line, because 2 is less than or equal to 4 times 2. So the shaded side I want to shade out is above the line. Now some students realise that intuitively, but if you're not sure, double check that you shade the correct side. Moving on to the next constraint, which is this one. Draw the line 5y plus 2x equals 10. The best way of drawing that, by the way, is look for the x-intercept. So when y is 0, x is 5. And if you look for the y-intercept, when x is 0, y is 2. So we're looking at this straight line here. Now I want 5y plus 2x to be more than 10. So you might see straight away that it's above the line that we want as our solution. Another way of checking, if you're not sure, is to test the origin. Is it true that 5 nothings plus 2 nothings is more than 10? Well, that is not true. So the origin fails the inequality. So the origin is on the side of the line that we want to shade out, because the inequality failed when we subbed in 0, 0. Just a couple more. Here's our next constraint. X plus y is less than or equal to 5. So you find your constraint, look for the y-intercept, look for the x-intercept and draw the straight line. We want x plus y to be less than or equal to 5. So again, if I just try the origin, 0, 0, is it true that nothing add nothing is smaller than 5? Well, that is true. So the origin is on the correct side of my constraint, so I shade out the side of the line away from the origin, opposite to the origin. And finally, our last constraint, find the line 5x plus y equals 5. Again, look for x and y intercepts, so it's this one here. We want 5x plus y to be greater than or equal to 5, and again you can see that either intuitively, if you test the origin, is it true that 5 nothings plus nothing is more than 5? Well, that is blatantly, clearly false, so the origin is not a solution to the inequality, so I shade out the side with the origin. Always check each line very carefully. If I put them all together now, we have that. They are the 6 constraints. Always shade out the unwanted region for each one as you're going along, and you should end up with an unshaded region, which is called the feasible region. Our solution is somewhere inside the feasible region. So let's have a look at this feasible region. Our objective is to maximize p equals 3x plus 4y. So what we'd need to do is, one method is to use a vertices method. We know that any point in the feasible region satisfies all the inequalities. We know that R is a polygon and it has 6 vertices. So one method is to go round finding all the vertices. One of the vertices must be an optimum solution. Now normally I would do all the vertices, but just for this maximizing problem I'm going to look at A, B and C. Normally I would do all 6 at the same time. I'll label them now, but we're going to deal with the other 3 in a moment. So let's look at the obvious ones. I can see straight away from my diagram that B is the point 2, 3. I can see that C is the point 3, 2. And for A, I can see the y coordinate is definitely 3. And if I sub y is 3 into this constraint, I will get the x coordinate is 3/4. So we're looking at a maximizing problem, so I'm going to focus on A, B, C. The maximum value of P is going to be one of these high vertices. So the first thing I'll do is say I'm looking at A, which is the point 3/4, 3, and I'm now going to calculate P. So P is 3 times the x coordinate, so that's 9/4, plus 4 times the y coordinate, which is 12, which gives me 57/4. So now we look at the point B, which is 2, 3. So P is 3 times the x coordinate, which is 6, plus 4 times the y coordinate, so that's 3 4s are 12, which gives me P equals 18. And C is the point 3, 2. So P at that point is 3 times the x coordinate, so that's 3 3s are 9, and 4 times the y coordinate, so that gives me 2 4s are 8, which gives me 17. Now in the exam I would carry on and do D, E and F, but for the purpose of this exercise we're trying to maximize P, and that is the biggest value of P. And therefore P, or shall I say maximum P, equals 18, and that will happen when x equals 2 and y equals 3. That is my maximum solution, and that is what the maximum solution would be for this linear program. So now we're trying to minimize P. So I'm not going to do A again, or B, or C. I'm going to focus on D, E, and F. So we're trying to make P as small as possible, so that P might be to do with wastage, for example. So I'm going to focus on these vertices. So D, I can see straight away from the diagram, is the point where x is 3, and if I sub 3 into this constraint, I will get y is 4/5. E is a little bit trickier to find, so E, I would need to solve I'd need to get these two constraints and the equality version of these two constraints and solve them simultaneously, and I would get E is 15/23, 40/23, and then F, likewise, I'd need to solve these two constraints together simultaneously to work out where F is. So if you're not absolutely sure where the coordinates are from the graph, you will need to solve simultaneous equations. 5/9, 20/9. Remember, we're trying to minimize P this time. So P at this point is 3 times the x coordinate plus 4 times the y coordinate, which is 61/5. P at this vertex is 3 times the x coordinate plus 4 times the y coordinate, which is 205/23. And lastly, at F, P is 3 times the x coordinate and 4 times the y coordinate, which is 95/9. And again, I would do A, B, C in the exam, so I had a full set. We're trying to minimize P, and the smallest value I can find for P is this one. So my solution is the minimum value of P is 205/23, and that happens when x is 15/23 and y is 40/23. It's worth noting here that there's an assumption in this example that x and y do not need to be integer solutions. Okay, so this is the non-integer solution to this linear program. In the next session, we'll be solving a graphical solution using the objective line method.